Alright guys, welcome to lesson 7.7. Today we're going to learn how to find various parts of a rational function. These are the parts we'll be looking for. And the reason we're doing that is because in our next lesson we're going to actually learn how to graph rational functions, and you'll need to know how to find all these parts to do that. So today we're just going to practice finding all of these parts, and we'll be ready for next time. So let's go ahead and start off with part A here. How do you find a y-intercept? You find the y-intercept the same way you find a y-intercept for any function, and that's by plugging in 0 for x. So if you plug 0 in for x, anything that you plug 0 into is going to basically go away. And so what you're always going to be left with is just the number without an x on the top and the number that doesn't have an x on the bottom. And in this case, I'm left with 3 over negative 12, which reduces to negative 1/4. And so this function would touch the y-axis at negative 1/4 on the y-axis. Okay, so go ahead and pause the video here and see what you guys get for student practice 1. And when you unpause the video, you'll see the solution. And this is what you guys should have gotten. The x is all, anything with an x just goes away because you're plugging in 0, which leaves you with 6 over negative 2, which is negative 3. So this function here would have touched the y-axis at negative 3. Let's move on to our next part that we want to learn how to find. To do that, we need to review some basic math facts here. 0 over 5, what does that equal? Hopefully you know that equals 0. 5 over 0, however, does not equal 0. 5 over 0 is undefined. It doesn't exist. You're not allowed to have 0 in the denominator. Okay? So, let's look at a rational expression. What number can I plug into the top here that will make this entire fraction equal 0? Well, as we said on the last slide, the thing that will make the entire fraction equals 0 is if the top equals 0. So if the top, which is x minus 1, equals 0, that means that when x equals 1, the function equals 0. Okay? So in order to get your y value to equal 0, your y represents the whole fraction. So in order to get the y value, which is the whole fraction, to equal 0, the top needs to equal 0. And what this tells you is this is the x value that will make the y value equal 0. And we have a name for that. It's known as a root. So whatever number will make the top equal 0 is a root. Now what value of x will make the fraction undefined? Well, the fraction is undefined anytime the denominator equals 0. Okay, so if this equals 0, then my fraction will be undefined. And therefore, if x equals negative 3, then my fraction will be undefined. Now, on a rational expression, whenever it is undefined, what that usually means is present is a vertical asymptote. So, if you want to find your vertical asymptotes, you set the bottom equal to 0. So now we know how to find two other important parts of our rational expression. Anything that makes the top equal 0 is a root, and anything that makes the bottom equal 0 is a vertical asymptote. Okay? Now, every once in a while, you might end up with a situation in which you have the same factor on the top as you do on the bottom. So let's say I had x plus 1 over x plus 1. That's really weird, but that's possible. Well, when this happens, the top and the bottom, technically you could think of them as canceling each other out. And so in that case, that means that the top does not tell you a root. So I wouldn't set the top equal to 0 and solve. And I won't set the bottom equal to 0 and solve either to find a vertical asymptote. Instead, what I'm going to do is we're going to cancel that factor out and just ignore it. But that factor still tells us something. And what is it? Well, remember how I told you the fraction is undefined anytime the bottom equals 0, and usually that means it's a vertical asymptote? That's what it usually is. However, if the bottom and top cancel, even though we're still not allowed to have x equals -1 in the bottom, because that's what would make the bottom equal 0, right? Even though we're still not allowed to have x equals -1, it's not a vertical asymptote when it's the same on the top and bottom. When it's the same on the top and bottom, that tells us what a hole is. And a hole is something like where whenever you have a graph, all of a sudden there's just a gap in it, and then it keeps going. Okay, it's kind of weird, but rational expressions have holes in them sometimes. And so, whatever makes the top equal 0 is a root. Whatever makes the bottom equal 0 is a vertical asymptote. But if the same factor's on the top and the bottom, that factor will tell you where a hole is at. It's not a it's not a root, it's not a vertical asymptote, it's a hole. So we have now a way to identify 3 parts of our rational expression. When you have a rational expression, the first thing we're going to do is we're going to factor it on the top and the bottom. And whatever makes the top equal 0 tells us what the roots are. Whatever makes the bottom equal 0 tells us what the vertical asymptotes are. But if any of the factors are the same in the top and bottom, that particular factor will tell us where a hole is located at on our graph. Okay, so let's go ahead and put this into practice and kind of bring it down to earth a little bit. So I'm going to write down example 2 here. So the first thing we're going to want to do is factor. So on the top, I would use the box method to factor that. If you use the box method to factor that, you would end up getting x plus 2 times x plus 3. To factor the bottom, you need to take out a GCF, which is -3, which would leave you with this. Okay? So, first of all, I want to ask you guys, do you guys see any factors on the top and bottom that are the same? Because if you do, that means it's a hole, there's a hole there. Well, no, I don't see anything. So in this case, we're going to say there's none. A hole would be if you had the same factor on the top as you do in the bottom, but we don't have one of those. So we don't have one for this particular function. Now let's go ahead and find the roots, the x-intercepts. Those are where the top equals 0. So to find my roots, I need to solve these two equations. X plus 2 equals 0 and x plus 3 equals 0. So I have one root at x equals -2, and I have another root at x equals -3. So this function has no holes, but it has 2 roots. It has 2 places where it touches the x-axis. It touches the x-axis at -2, and it also touches the x-axis at -3. The last thing we want to look for is we want to look for our vertical asymptotes. And that's where whatever's on the bottom equals 0. And so I only have one factor that I can actually set equal to 0, and that's x plus 4. And so if I solve that, I get x equals -4. So this function has no holes. It has 2 roots and 1 vertical asymptote. Okay? So factor is first, then you look for the holes, then roots, then vertical asymptotes. Let's look at number 2 for a second example here. All right, so once again, we have to factor first. So on the top, I see that there's a GCF here, so I'm going to start by taking out a GCF. If I do that, that's going to leave me with x squared minus 2x minus 8. And then I'm going to do the box on what's left. So if we do the box on what's left, we will have x, 4, 2. There we go. All right. We need to do the same thing on the bottom now. I do see a GCF in there. I can take out a -4. which leaves me with x squared minus x minus 6. And then I'm going to factor this trinomial using the box method once again, which would give me x minus 3 plus 2. All right, so there I factored it completely. Both of them had to be factored using two strategies, GCF and box method. All right, now I'm ready to identify the parts. So do I have any holes? A hole is what happens anytime you have a factor that cancels out. As you guys can see, the x plus 2 cancels out. And so this graph will have a hole in it at x plus 2 equals 0. And so that means that at x equals negative 2, this graph is going to have a hole in it. Next, we're going to look for our roots, also known as x-intercepts. The x-intercepts happen anywhere where the things on the top equal 0. We're not going to include this one because that was a hole, right? We ignore that one now. That's why we start by looking for the holes first, so we know to ignore it when we get to this step. All right, so I have two factors on the top, x and x minus 4. So that means that x can equal 0, or x minus 4 can equal 0. And solving this one here, we get x equals 4. So this function has two roots. It's got a 0 and a 4 for a root, and it has one hole at negative 2. Next, we need to find the vertical asymptotes. You can't set 4 equal to 0 because there's no x in it, but we can set this one equal to 0. So it's going to have a vertical asymptote at x equals 3. Okay? Now, I'm going to draw a picture of this. I don't want you guys to put this in your notes because the picture's probably wrong, but it's going to have the right stuff in it for what we know right now. Okay, so I just want you guys to get a visual image of what we're looking at. We have a vertical asymptote at x equals 3. So I know that at x equals 3, there's a dotted line here that my graph cannot touch. I also know that it touches the x-axis at 0 and at 4, which would be right here and right here. And interestingly, it has a hole at negative 2. Now, I don't know where that hole is going to be located exactly, but I don't know how high up or how low down it's going to be, but there's a hole there at negative 2. Now, if we were to try graphing this function, I believe it would look something like this, but I'm not entirely sure. Okay, because it touches these roots, and it can't go through this asymptote here. And the last thing is the hole. Now, I haven't drawn the hole yet because I didn't know where the hole would be, but if this is what the graph actually looks like, then we would have a hole like right about here, right above that h that I put on there. At x equals negative 2, there would be a hole in this graph. So that's what we're going to be doing tomorrow, is we're going to be learning how to turn the facts that we find into a picture of the graph. But for today, you don't need to do that. I'm just giving you a sneak preview. So let's review one more time then before we get started on your student practice. And here we go. Step 1, factor your polynomial. Next, look for the pieces that cancel out. Those will tell you where your holes are located. Anything that's left in the top, set it equal to 0 and solve. That tells you the roots. Anything that's left on the bottom, set that equal to 0 and solve. That tells you where the vertical asymptotes are. So there you guys have it. And here's a student practice for you. Go ahead and pause the video. And when you unpause it, you will see the solutions. Okay, there you guys have it. Number 1's pretty straightforward, but number 2 might need some explanation for you guys. So on number 2, you could take an x out of the denominator, and when you do that, you can actually cross an x off the top and the bottom, and that means that at x we have a hole. So x equals 0 is a hole. Now, since I crossed that x off of the top, all that's left in the numerator now is a number 2, which means there's nothing I can set equal to 0. You can only set things equal to 0 if there's an x in it. And so now, since there's just a number, there's nothing in the top that I can set equal to 0, which means that there are no roots. The vertical asymptote, I can set x minus 1 equals 0 and solve, and you get x equals 1. That one's not too weird. But the first two there might have been a little strange to you. But there you guys have it. A little bit of a shorter lesson today, but that's all we're going to be discussing. And so we'll go ahead and call it a day there. We'll see you guys next time.